All right, hello everyone. I'm Mason Neuman from Washington University in St. Louis. I'll be talking about the composition of the Apollo 17 double drive tube 73001, 73002. This is just some background information that I think we're all familiar with at this point, but I just want to highlight some questions that we can hopefully answer by looking at the compositional data of the double drive tube. The first being, does the light mantle originate from the upper slopes of the South Massif? Has there been any post-depositional activity of the light mantle deposit? And can we say anything about the depth of the light mantle deposit? Is the double drive tube penetrating all the way through? So the samples that we analyzed for this study were given to us after Dick Morris measured the ISOBS. So that was 37 intervals from pass 2 of 73002 and 67 intervals from pass 2 of 73001. These were all the 50 milligram samples of the less than 1 millimeter sieved fractions. And we determined the composition, the concentration of 47 different elements for each of these intervals at WashU. The methods we used for this were first the quadruple ICP-MS, and I have the list of all the elements that we determined up there. This first involved dissolving each sample, and we ran the solutions through the ICP-MS at different dilution factors for major and trace elements. These were compared against a USGS rock standard calibrations. And additionally, we measured some other relevant lunar samples such as 73131 and 7321 as a quality check and a point of comparison for the double drive tube composition. The next method we used was fused bead electron probe microanalysis. So each of those samples, I took a few milligrams and fused the powder into glass bead, and we measured those glass beads on the electron microprobe. So this gave us major element data, including silicon, which we were not able to get with the ICP-MS, and this also provides an additional check on our ICP-MS data. Off to the left, there is just a backscattered electron image of one of these fused beads that I created, and you can see that it's a nice homogeneous glass. And for each of those beads, we took 10 to 15 spot analyses. And the plots on the right, I'm just comparing our results from the ICP-MS versus the fused bead data. And we can see that for iron and titanium, we have pretty excellent agreement between the two methods. These points are lying on this one-to-one line between the two methods. So we'll just jump straight into some of the results here. First, I'm showing a few elements with affinity for mafic minerals. So their concentrations on the horizontal axis versus depth beneath the surface on the vertical axis. And I have it split into 73002 in the top, separated by that dashed line, 73001 underneath. And we can see that these particular set of elements follow a similar trend with elevated concentrations near the surface. And we also have corresponding spikes at certain depth intervals. We can also see a slight increase in FeO content near the bottom. But however, 73001 is more homogeneous with depth than 73002. So just another set of these elements with affinity for mafic minerals, manganese, vanadium, and chromium. We can see the exact same trends that we saw for the last set of elements. Next up, looking at some siderophile elements, cobalt, nickel, and copper. We can see that there are even larger spikes in these elements. They typically occur at matching depth intervals. However, there's some outliers, especially for copper, that show spikes, but not corresponding spikes in cobalt or nickel. These elevated levels of siderophile elements are likely the result of a meteoritic component addition. We'll talk a little bit more about that in a little bit. Lastly, here I'm showing potassium, sodium, and zinc. And this is something I found when I was just looking through the data. We can see slight increases with depth for some of these moderately volatile elements, especially sodium and zinc. And if you just take a quick look at their 50% condensation temperatures as a gauge of their relative volatilities, we can see that zinc, the most volatile, has the largest increase towards the bottom of the core, followed by sodium, and really not so much of an increase for potassium, the least volatile of those three elements. So potentially we have preservation of other volatiles at depth. Just an idea I had while looking through some of the data here. Next up are the rare earth patterns of 73002. I split these into 3 centimeter averages just to make the data a little easier to look at. And the takeaway from this is just that the upper portion of the core with the red line here is distinct from the lower portion of 73002 shown in the orange and yellow lines there. And then we have these two other lunar samples that I measured, 73261. Its composition is very closely matching the composition of the upper part of 73002, and then 73131 has a composition very close to the lower portion of 73002. So what did we do with all this compositional data? We did a lithologic component analysis, and this was an error-weighted linear least squares approach from Kortev and Kremser, 1992. And essentially, we took 5 mixing components to explain the composition of each interval based on 26 different elements. So we were calculating what proportion of these different components were needed to explain the composition of every interval of 73001. And the components we selected were Apollo 17 high titanium Mare basalt, north acidic norite, neritic impact melt breccia, orange glass, and then a volatile-free carbonaceous chondrite component. We selected CM chondrites for this. So here are the results of this mixing analysis. We'll just start off on the left here, the high titanium Mare basalt. We can see that the surface has a relatively higher proportion of this high titanium Mare basalt that sharply decreases in the first 10 or so centimeters, followed by maybe a slight increase towards the bottom and then a sharper decrease at the bottom as well. Next up, the neritic impact melt breccia has a relatively consistent value through the first 20 centimeters, followed by a small increase going down the core. And the north acidic norite shows an increase near the surface. However, that turns into a slight decrease as you go down in depth. And then the volatile-free CM chondrite component shows a few percent throughout the core, again with those large spikes explaining some of those elevated nickel and cobalt concentrations that we saw earlier. Lastly, the orange glass again shows a few percent, mostly at the surface of the core, gap in the middle, and then we have a couple more percent at some intervals towards the bottom. So what do these components tell us about the actual core? If we take a look at the high titanium Mare basalt, we see this elevated concentration near the surface, and that's indicating to us recent mixing of valley floor soil, likely from impacts. So this kind of matches up with the that light or dark and light contact near the surface. So we're seeing a higher proportion of basalt in that darker region of 73002 at the surface. And then from this, we can also say that the drive tube did not penetrate the underlying pre-avalanche regolith, because in that case, we would expect to see a larger increase in the basalt component at the bottom, which we did not see. Additionally, if we take a look at the neritic breccia to neritic breccia and north acidic norite ratio, this would indicate that the drive tube sampled avalanche material originating from the upper slopes of the South Massif. And this is due to the fact that the north and south massifs are compositionally stratified with a higher neritic breccia content at higher elevations. And so the percentages that we're seeing here are higher than what we saw for 73131. This was a friable regolith breccia from the lower slopes of the South Massif, which had a percentage of about 37. So we're getting even higher percentages than that for the rest of the core. So we're concluding that the sampled light mantle deposit originated from even higher elevations on the South Massif. So just to conclude here, we saw some correlated elemental variations, and we were able to link these to specific lunar lithologies. Saw that the large Highlands component was consistent with an origin from the upper South Massif. And we also saw that mixing after the light mantle in place, we saw mixing after the light mantle emplacement with this elevated basalt component near the surface, potentially from valley floor soil addition from nearby impacts. This was limited to the top 8 or so centimeters. So in the end, we're left with concentrations of 47 different elements for every half centimeter. We use that for the mixing model. In addition, for the I sub S over FEO, and we have potentially many other applications for all this compositional data. So with that, I'll end. Thank you.